Welcome back, guys. Today we're going to be taking a look at IMO 2016 G5. On a side note, this was actually the first G5 I've ever solved, just yesterday actually, so I'm quite proud of that. And IMO 2016 was hosted in Hong Kong, so that's also pretty interesting. In the problem, we have D as the foot of perpendicular from A to the Euler line in a triangle ABC. We have a circle with center S passing through A and D, and it intersects the sides AB and AC at X and Y respectively. We let P be the foot of altitude from A to BC, and M the midpoint of BC. We want to prove that the circumcenter of triangle XSY, which we will call Z, is equidistant from P and M. Before we get started, I want to note that there are actually only two official solutions to this problem, and so the solution I'll be presenting today is entirely original. While this solution is still a bit lengthy, considering it is a difficult problem, I find that it is a lot more intuitive and human, if you will, than the other two solutions. And hopefully, after you're done with this video, you will see that the same way. Okay, so let's get started. We have, after triangle ABC is fixed, we actually also have a bit of freedom with the point S, because it can actually be anywhere on the line, on this line, which is the perpendicular bisector of AD. And then we eventually want to prove that the point Z lies on the perpendicular bisector of PM. And so what's interesting here is we might notice that there are a lot of perpendicular bisectors and midpoints and stuff. So what might be helpful here is a ×2 homothety. Whenever we have perpendicular bisectors, midpoints, a ×2 homothety can always help because we can transform lines and midpoints into something a bit more tangible. For example, if we perform a ×2 homothety centered at A here, the point S is originally a random point on the perpendicular bisector of AD, but now this line will map to the Euler line, and so instead S will just be a random point on the Euler line, which is a lot easier for us to handle. And then we can have the point Z after ×2 homothety. Since Z should lie on the perpendicular bisector of PM, this line should map to the perpendicular bisector of BC, or like the line passing through M that's perpendicular to BC, which is actually also just OM here. Okay, so that's pretty cool. And so what we can do now is we can actually rephrase the entire problem. So let's say we just have our original triangle. Of course, now instead of picking a point S on the perpendicular bisector of AD, we just pick a random point S on the Euler line, as we mentioned before. And so now we can draw a circle centered at S, passing through A, and then intersect side AB and AC at X and Y. And then we have the center of the circle SXYBZ, and instead we just want to prove that OZ is perpendicular to BC. Essentially what we've done is we've done a ×2 homothety centered at A, we've applied that to the point S, to the point X, to the point Y, to the point Z. Notice that we have O, H, B, C, etc. They're all fixed. We're just applying to these variable points right here. Okay, so now the problem is actually quite a bit simpler. The reason being that, for example, we don't have P and M, we don't have D. Essentially, we just have a lot of points reduced. Right now, we only have A, B, C, S, X, Y, Z, O, and H. That's like, what, 8 points? I also added the point M here, which is not the same as the other M. It's just naming conventions. But we will get to that later. Okay. So, actually we will get to that right now, because let's construct this point M. And what M is M is actually the reflection of A across the Euler line. It's over here. Well, the reason being, for example, OA is equal to OM, and SA is equal to SM. So this is the perpendicular bisector, so we just reflect it over there. Okay, and the reason we are constructing the point S is that we notice that the point M is the intersection between two circles, and the other intersection is A, and you see A lies on some lines. Those are really bad lines. A lies on some lines. So what that is hinting at is actually McQuell points. This is a bit more advanced theory, but we actually don't need a lot of concepts. We just need a simple fact about spiral similarity with these circles, which can be quite easily proved, so I'm not going to go over that. But essentially, from this, if we look at B, X, C, Y, we see that BX meets CY at the point A, which is also the intersection of these two circles, and we see that XYA, the circle, passes through ABC at M. So what this means is that M is the McQuell point of the quadrilateral BXYC. Well, this is just a fancy way to say that there exists a spiral similarity mapping centered at M, mapping BC to XY, or BX to CY, but let's just say BC to XY, or XY to BC. And, well, like I mentioned, we can easily prove this with angles. For example, we can prove that these two triangles are similar using angle tracing with the circles, but I'm not going to go more in depth on that. But the reason we want the spiral similarity is that there are actually some more similar points in this spiral similarity. So what we're going to focus on is just the spiral similarity mapping XY to BC. For example, if we take a look at the point S, we look at this triangle. This is an isosceles triangle, SXY, with angle XSY is equal to 2 times angle XAY, which is 2 times angle A. And then if we look at BOC, BOC is also an isosceles triangle, and angle BOC is 2 times angle BAC, which is also equal to 2A. Therefore, we have that the triangle SXY and the triangle OBC are actually directly similar. And so if we envision or imagine the spiral similarity, the point S should map to the point O under this spiral similarity. Okay, so then we are thinking, maybe let's also consider the image of Z under the spiral similarity. So what is Z defined as? Well, Z is the center of the triangle SXY, which under the spiral similarity gets mapped to the circle OBC. So let me quickly draw this circle. Hey, that's not a bad circle. And let's call this point D. So Z will map to D. And note that since DB is equal to DC, D also lies on the perpendicular bisector of BC. And since we want Z to lie on the same perpendicular bisector, it is equivalent for us to show that OZD are collinear. And we are going to go through a quick demonstration of false positioning to get some more useful information, or convert this into something more tangible, because OZD, that's a bit too many points and we don't really want to deal with all that stuff. Ideally, maybe we can remove S, X, Y, and all that stuff, because after all, they're just images of our ABCO under a spiral similarity. Okay, so what we're going to do is let us assume that DZ meets the line SO at a point called O prime. Since we want these three to be collinear, we want O prime to be O. Okay, so we also know that, first of all, M, the spiral similarity from M that maps S to O also maps Z to D, which means that these two triangles are similar and we have a spiral similarity between them. And so let me just draw this, and let's say this is O prime. By the property of McQuell points and spiral similarity, which again we can quickly prove using angle tracing and similar triangles, we know that actually MS O prime and Z should be concyclic. Yes, MS, O prime, and Z should be concyclic. Well, if you want a bit of a more intuitive thinking, well, the reason is, for example, if we intersect this here, then S and O are corresponding, S and Z are also corresponding, but S has nothing to do with D, and then O and S are corresponding, O and D are corresponding, O has nothing to do with Z. For example, if we pair up D and Z and S and O, we get the intersection point here. And so we have that, for example, DS, which are the opposite points, DO, the opposite points, we have that DO, O prime, M should be concyclic. And we also have that ZSOM should be concyclic. So ZSO prime M. But since we want O prime to be equal to M, it is equivalent to show that MSOZ are concyclic. Okay, well, that's cool, but I actually just realized something, which is that when I was in my solution, I actually did a long angle chase, which I can put it up there, but I did a long angle chase to prove that MSOZ being concyclic is actually equivalent to another condition. But now that I'm talking to you guys, I've realized that there's actually a more simple way to arrive at the same conclusion. In spiral similarity and McQuell points, we say that it is equivalent to prove that MSOZ are concyclic. However, I also mentioned that it is equivalent to prove that DO prime OM or that DO prime OM are indeed concyclic. But since we want O prime to be equal to O, we just want DOM, the circle DOM, to be tangent to the Euler line right here. Okay, so we can phrase that in a bit of a nicer way, which I'm going to scroll down here. We want to prove that the circle MOD is tangent to the Euler line, which I'm just going to call it HO right now. Okay, so our original condition is equivalent to proving this tangency, which is actually quite nice. And one really nice thing about this, obviously tangency is nice because we have less stuff, but what's even better is that, as I previously mentioned, S is removed, X is removed, Y is removed, Z is removed. Everything is removed. All we have is actually just MOD, where M is a reflection of A across the Euler line. So now we only have what? 1, 2, 3, 4, 5, 6, 7. We only have 7 points left in the diagram. You see, this is one of the key takeaways, which is that, for example, we can perform these transitioning of our conclusions. For example, the conclusion we want is that OZD are collinear, but we can convert this into some other conclusion, for example, that the circle DOM is tangent to the Euler line. And with these other conclusions, sometimes, as we see this time, we can actually simplify the figure by removing some unnecessary points that we no longer need. Here we removed all of the X, S, X, Y, Z, and so we just wanted to prove that the circle MOD is tangent to HO. Okay, so let's see how we can do that. Well, to prove that MOD is tangent to HO, obviously one thing we can think about is angle chasing, and the other thing we are thinking about is power of a point. But power of a point doesn't seem to work very well here, and so maybe we just want to do a bit more of angle chasing. Okay, so for example, if I were to connect this, we just want to show that this angle is equal to this angle, or that angle equals this angle. But let's see which one should be a bit nicer to prove here. And I'm just going to connect AO. Obviously, we can think about, for example, a reflection of D across this, so we get a similar triangle, or not a similar, a congruent triangle, because they're just reflections of each other across the Euler line. And for example, we should probably try the other angle in this case, as it will turn out the other angle is a bit nicer to prove. We want to prove that this angle is equal to this angle. We know that this angle is actually just also equal to this angle since they're reflections of each other. And what we're going to do is we're going to extend this thing down here to a point, let's say point P. So we're going to prove that these two angles are equivalent. So we can just take their supplementary angles, which are these two angles, and we want to prove that these two angles are equivalent. But what's interesting is if I draw AP down here, we notice that PA and PDM are actually, these two lines are symmetric about the Euler line. And so these two angles are actually also equal. So if we notice, triangle PDO should be, well, we haven't proved it, but we want it to be similar. We want these two triangles to be similar. And if we can prove that these two triangles are indeed similar, then we have proved that this angle is equal to this angle, and consequently this angle is equal to this angle is equal to this angle, which means that they're tangent, which is exactly what we wanted. Okay, so now we can rephrase the problem yet again. This is like the third time we're rephrasing it. We'll do a summary later, but we will count how many times we rephrased it. But for now, let's just draw MD, intersect this thing at P, and I'm going to draw some lines. My lines are kind of squiggly, but that's fine. So we want to prove that these two triangles are similar. And here we actually have to use a little bit more of theory, which means that, okay, if PDO and POA are indeed similar, by definition, this means that P should be the O Humpty, or actually, I mess up the names, the O Dumpty point, yes, the Humpty and Dumpty points, the O Dumpty point of triangle OAD. We have that this is similar to this, is equivalent to this. And while we don't need to use much theory, but we can recognize this, and something we're going to use this to help us is that basically there's only one O Dumpty point of OAD, which means that there only exists one point P in this entire plane such that PDO is equal to POA. So P is unique. And we want to show this unique point P lies on this line OH. And why is that sufficient? For example, if we prove that this unique point P does indeed lie on the line OH, then we can think about dragging points across this line. And since we want that angle APO to be equal to angle OPD, and actually let me use a bit of a P prime. Okay, in order for these to be similar, we know that angle AP prime O has to be equal to angle OP prime D. However, we also have that angle AP prime O is equal to angle OP prime M, and so we want angle OP prime D is equal to angle OP prime M, which means that we want DMP prime to be collinear. Which means that if we have proved that the Humpty point lies on this line, the Dumpty point, if we have proved that the Dumpty point lies on this line, then the Dumpty point can only be here, as the Dumpty point D and M have to be collinear. Okay, so, well, this is a more of a minor transition, but again, we have actually transitioned the problem once more. Now we are seeking to prove that the O Dumpty point, and by the way, you don't have to know anything about Dumpty points. The only reason I use this was to show the uniqueness of the Dumpty point. The O Dumpty point of triangle OAD lies on OH. And for those of you that are a bit more impatient, we're actually almost nearing the end, so just hang in there. Okay, so the strategy we are going to take or adopt here is that we are going to construct the O Dumpty point P prime first, and then we're going to show that P prime, H, and O are collinear. actually we don't even need P prime. Let's just construct the Dumpty point. Construct the Dumpty point, we call it P, and we prove that P, H, O are collinear. Okay, so let's construct the point P right here first. And so, since we are constructing it, we already know that PDO and POA are collinear. For example, this angle is equal to this angle. And the strategy we're going to adopt here is actually similar triangles. And what do I mean by similar triangles? Well, we already have a pair of similar triangles, but we can actually find out a bit more about this triangle. For example, let's take a look at the angle OPD. We know that the angle OPD is 180 degrees minus angle PDO minus angle POD. But we know that PDO is actually also equal to POA. So this is just equal to 180 degrees minus POA minus POD, which is 180 degrees minus AOD. And we actually know exactly what AOD is because, well, let's think about this. AO is this diameter, and then if we draw a line that's parallel to BC here, and then obviously these two are perpendicular, and so this angle is actually just equal to this angle, which is equal to this angle plus this angle, which is C plus, what should this be? 90 minus B. So this angle is C plus 90 minus B, but we obviously have to add another 90, so this should be equal to 180 degrees minus 90 minus B plus C. And by the way, I'm assuming without loss of generality that the angle B is greater than the angle C. So 180 degrees minus this minus another 90 degrees, or plus another 90 degrees. And this should be equal to angle B minus angle C. Okay, we know that angle OPD is equal to angle B minus angle C. And I'm going to use my very advanced tool of lasso select so I can move this thing up here. Isn't that just so cool? I'm such a funny guy. Okay, and so we know what this angle is. Okay, that's nice. But what's even nicer is we also know what this ratio between these two side lengths are. We can look at these two side lengths as side lengths in the triangle POD, but we can also look at them as corresponding side lengths in the similarity of PDO and POA. For example, the line PD corresponds to PDO, and the line PO corresponds to POA. So PD over PO is just the ratio of the similarity between the triangles, which is also equal to DO over OA. So let me write that down. PD over PO is equal to DO over OA. And look, we have all the information for this triangle that we possibly need. We have an angle and we have the two sides. And so we can actually just use SAS here, and we can maybe even find a pair of similar triangles for ourselves. Okay, well, let's think. What has an angle of B minus C? Well, if we think about it, for example, maybe if we draw this right here, what is this angle? Let's think. So we know that this point is the midpoint of the arc BC, and we know that this arc is actually B minus C over 2. You can check for yourself. And so this big angle is just B minus C, and that angle is actually B minus C. That's really nice. But the thing is, we also want the ratio of the side lengths to be right. But obviously this triangle, the ratio of the side lengths don't look right? So what we're gonna do is, that is a very curly line. What we're gonna do is we're gonna draw this thing down here. Let's call this A1. It looks like P, A1, D are collinear, and they indeed are, but we're not gonna need them in the solution. We know that OA and OA1 are symmetric about the line OD, and so this angle is also B minus C. But what's nice here is we also have that OD over OA1 is equal to OD over OA, which is equal to, as we've seen here, PD over PO, and this is also B minus C. Hence, we have obtained a pair of similar triangles. which is we have obtained that PDO is actually similar to ODA1. Okay, that's really nice. And the purpose for doing this is, first of all, PDO is similar to POA, and so we actually know that the angle POA right here is equal to this angle, is equal to angle PDO, which is also equal to angle ODA1. So maybe we can just show that HOA, the angle HOA is actually equal to the angle ADO, A1DO. Because if we show that HOA is equal to angle A1DO, we also know that angle A1DO is equal to angle POA. So HOA equals POA, which means that PHO are collinear, and that is indeed what we want. But there's one final piece of suspicion here, which is that these two triangles, AHO and OA1D, they look way too similar, especially with this equal angle. And actually, it's not even going to be a hypothesis anymore because we can confirm it. We know that this angle is angle B minus C, and this angle is also angle B minus C, and since these two lines are parallel, we can transfer this over, so this is angle B minus C. Okay, we already have a pair of equal angles. Since we want these two angles to be equal, these two triangles obviously have to be equal. And so what we actually need to do is, since we already have a pair of equal angles, we just need to prove that AO over AH is equal to OD over OA1. And by the way, AO and AO1 are both the radius of the circumcircle, so I'm just going to write it as a radius just so it's a bit nicer. Okay, so let's take a look at OD over R first, because that looks quite easy to tackle. For example, we can transfer R from OA1 to OB. And let me just zoom in on that triangle. This should be an isosceles triangle with this length being, okay, this is O, this is D, and this is B. This length right here is R, and this is the length OD, what we want. And we also know that this angle is actually just, what is this angle? This angle is angle BOD, which is half of angle BOC, which is angle BAC. So this is just angle A. And we can actually find this angle quite easily using trigonometry. For example, since this is an isosceles triangle, then this length should be half of this total length. And so we can express this length as with these two quantities. For example, with trigonometry, we know that cosine A is equal to R over 2 over OD. And so we have that what we eventually want is OD over R. So maybe we can flip this. I think that might help us a bit because we don't really want a secant. Like a secant is quite ugly. Anyways, R over OD will be equal to 2 cosine A from that. Okay, so all we have to prove is that AH over R is also 2 cosine A. And so since H is the orthocenter, we've never actually used the condition of the orthocenter. And hint hint, that means we have to use the condition of the orthocenter now. Okay, one of the most prominent things about the orthocenter is that if you reflect it over the sidelines, then it should also lie on the circumcircle. For example, if I reflect AH over the side AC, we end up with this point, which I'm going to call H prime. And since it's a reflection, we have that AH is equal to AH prime. And we want to show that AH over R is equal to A2 cosine A, which means we want to show that AH over 2R is equal to cosine A. But this looks so familiar, AH over 2R, that's just the extended sine law, right? We just have to find the angle that this arc subtends. Okay, and that should not be that difficult. For example, we can look at angle ACH. We have that, or ACH prime. ACH prime is equal to angle ACH, which, for example, if we draw a perpendicular down here, this is A, so ACH is 90 minus A. This is just 90 minus A. And so AH over 2R is sine of 90 minus A, which is indeed cosine A as we desired. Therefore, we have indeed shown that these 3 points are collinear, and if we trace that all the way back, it should eventually prove this claim, assertion. Okay, well that was that was quite a long problem. So let me summarize it because I think it's really rich in takeaways. So what we did is, first of all, we rephrased the problem by changing our perspective. We took a homothety centered at A with times 2 so that we actually arrive at a different configuration, and we eliminated the need for some points such as D, P, and M. And here we're still not satisfied because we actually used McQuell points to change our original conclusion, our assertion, which is that OZD are collinear. We changed that into something different. For example, proving that the circle MOD is tangent to the Euler line. And the benefit of this is that we remove even more points. We remove points S, X, Y, Z, and we get it down to this configuration with only 7 points, and we just want to prove a tangency, which is a lot easier. For example, here we can use the Dumpty point P, and we just use some similar triangles to prove that these angles are indeed equal. So, as you've seen, the common recurring theme across this problem is to keep changing your perspective. So you keep changing your perspective, you keep simplifying the problem, you remove points, and eventually you just get it down to a really simple problem. For example, proving that 2 angles are equal via similar triangles. And so you just want to keep doing this process of reducing the problem down. And the direction you probably want to go in is just to try to reduce the number of points. That's what you want to keep taking a look at. Whenever you do a problem like this, you want to look, is this point really necessary? Is there some way that I can remove this point? Can I change the assertion to something that does not need this point at all? Can the information in this point be encoded to something else? So that's the most key insight from this problem. Thank you.